So this is the general geology and the stratigraphy. So the geological boundaries, the western part is the Keter and the Suleiman Fold Belt. The northern part is the Suleiman 4D and Punjab platform, and the southern part is the Jacobabad Highs. So coming towards the petroleum play, the source is actually the Sember Formation. It is the proven source in the lower Indus Basin. The seals are the upper Guru Formation shales, and the reservoir is the lower Guru Formation. And as you can see from this stratigraphic interval that there is actually a lot of heterogeneity present within the lower Guru. You can see that there are intervals of sand, shale beds present within this formation. So this is a diagram of the schematic that we used for the creation of the geocellular reservoir properties. So it is actually twofold. The first is the petrophysics part, and the second is the seismic data interpretation part. So for the petrophysics, first of all, we actually interpreted the logs and calculated our desired facies, the reservoir facies, the wet sand, the hydrocarbon bearing sands at the shale. And then concurrently on the other side, we also used the seismic data, and we modeled the horizons, and then after modeling the horizons, we used a continuous wave transformation. So what it does is it actually splits a wave into three principal components of frequencies: the real, the imaginary, and the magnitude. And from there, what we did was we actually used the deep neural network in comparison from the petrophysical analysis and the continuous wavelet transformation features. And what we did was we established some kind of a relationship using the deep learning algorithm ResNet. And from there on, once the relationship was developed, it would populate the entire grid, the seismic grid, with 3D cellular properties. So this is again the methodology in a little bit more advanced workflows. So as explained previously, the well logs were used, DT, GRO, and fire and deep resistivity for petrophysical analysis. Hydrocarbon bearing facies were selected. Then seismic data was used, horizon marking, reservoir zone selection. Then continuous wave transformation was applied, and then features were extracted. And again, both of these were used concurrently with in the deep learning algorithm to specify the features and establish some kind of relationship using the deep learning algorithm. And from there, grids were established, and the geocellular properties were populated on the grid. So before moving towards the analysis, this is actually the outliers and the inliers in the data. This is just one example. We actually trained 3 wells and used 2 wells as blind wells for interpreting whether our work here is accurate or not. And as you can see that in the inliers, right, they follow all the other logs, the log responses from the other wells. So this is actually showing you. So why did we do this step? We actually did this to provide a little bit of more consistency to our approach for petrophysical analysis. So this is the pair plot analysis before and after the removal of the outliers. As you can see that after the removal of the outliers shown here, the clusters become much more better as compared to before the removal of the outliers. As you can see that the wet sand, the hydrocarbon bearing sand, and the shale facies are present and in a much more consistent way than present than shown in the previous pair plot analysis before the removal of the outliers. So this is a small diagrammatic of the ResNet architecture. So what it does is it uses a series of convolutions to specify, to establish some kind of a relationship between our petrophysical analysis and the CWT technique that we are actually using on the seismic. And what it does, as it passes through different convolutions, it develops some kind of a relationship. And the final fully corrected layer is actually the thing that we are most interested in. It has a high weightage. And as it passes through the entire ResNet, when the weightages are, when it falls to in the negative weightages, the ResNet would automatically discard them and move towards the next layer. For example, if I may say some, if it would make some relationship with volume of shale, effective porosity, SW, and facies, and it would consider those along the CWT trace, and it would create that one convolution network. And then it would pass it through other fine-tuning, BN, the batch normalization, the ReLU activation function for nonlinear conversion, and then the max pooling to create a better correlation for different for this ResNet architecture. So these are the machine learning algorithms used for outlier removal and the QC of the data. As you can see that the extra-tree regressor is performing far better than any other algorithm present here. About 94% R2 or correlation factor is present here. And the mean absolute error, the mean square error, and the root mean square error are also minimum in this case. So the time, as you can see, it takes about 0.18 seconds to train, but we can actually sacrifice that for a better consistency of the for the extra-tree regressor algorithm performing here.